thanks, Linus, for the introduction, and I also thanks for this number theory web seminar invite me to give this talk. And today I'm going to talk about some of my work with joined with Jason Bell uh, and his student Hossain and Khoa Nguyen and Umberto Zannier. And let me start from the integrals because actually my main topic is symbolic integration, which is about how to compute the integral by computer. But let me start with this. I think this is the first rational transcendental dichotomy theorem you can see easily. So this is a quite a well-known fact. So if you're given a rational function over the complex numbers, and if you think about the indefinite integral, and this actually the output is either a rational function or a transcendental function, because this will, if it's not rational, then the logarithm will come, and this becomes transcendental. So you will never get a algebraic function from integrating a rational function. So I think that's the first rational transcendental dichotomy theorem. And I think it's always the gene to have such kind of dichotomy theory in number theory, because, for instance, if you can show zeta 3 is irrational, this implies transcendental, and then that's pretty nice. But okay, let's see. Actually, from the integral, you can also get some dichotomy theory in numbers. For instance, in 1971, think about this integral. This is the definite integral of a rational function with rational coefficients. If the endpoint a, b are both rational, and then you by using the Baker's theorem, I think about the problem prove that actually this definite integral will either be rational number or transcendental number. So you can also get this kind of a rational transcendental dichotomy theorem in number theory for numbers. And that's the about integrals. And another source of this why we care about such kind of theorem, I think one of the things close to the so-called Polyak-Cantor theorem. So this is a continuing about this rational integrals. So even rational integral there are a lot of things we can say. So the problem is given a rational function and how you detect this integral is rational. In general, it's rational or transcendental, but how you can figure out the situation. And there are some arithmetic conditions which will make these things rational. For instance, if you have a rational function, if you can expand this rational function as a power theory with integer coefficient, and here the integer coefficient is arithmetic constraints, which is important. And then in general, when you integrate this rational function, you will get a non-rational. But if you impose this arithmetic condition, say an is divided by n plus 1 for all n. So which means if you integrate this power theory item by item, if you still get, in general, you will get, when you integrate item by item, you get the coefficient divided by n plus 1. If you still get the integers coefficient, then you can show that this actually is rational. So this includes the log. And this is actually follow from a very well-known fact by Polya. So which Polya show that if you have a power theory with integer coefficients, and this theory is rational, and if and only you can show that the coefficient is globally bounded. I will not give the definition for this, but basically this means you have a non-trivial convergence rate and radius. And another condition is if the derivative of this is rational, and then the original is rational. So that's the proof of this. And there's a more stronger result, which is about algebraic functions. In general, the same. Given an algebraic function, the integration of this is not algebraic, may not be algebraic, will become transcendental. And then there's also a result by Underhe by imposing some arithmetic condition, and then you can show this is algebraic. And for you can enlarge the coefficients. The coefficient taken from a number field. And then this Polya result can be extended to the algebraic case. This result is quite interesting. So,
Shaoshi, just a question from Vadim Tsudilin. Is there a typo there in the previous theorem? Please, Polya and Cantor, this is that of the I should be an X.
Oh, sorry. Yeah, you're right. Yeah, that I was prepared this. Okay, thank you very much. And another kind of rational transcendental dichotomy theorem is about Mahler function. So Mahler function is appear in the transcendental number theory. So let me give a definition for this kind of special function. So this is basically is the power theory over complex numbers. And if it is called the key Mahler, if they satisfy the following special functional equation. So this is AI to this is the polynomial coefficient. This is a functional equation, and if such kind of non-trivial function equation exists for fx, then we say this is key Mahler. And there is a result due to Nishioka, and say that actually for Mahler function, you have this dichotomy theorem. It's either rational function as a theory and or transcendental. So it cannot be algebraic, irrational algebraic function. And also there is a kind of number theory analog of this dichotomy theorem, which is for the automatic numbers. So this is actually automatic numbers actually very close to Mahler function. So this is for any real numbers, you can expand this real number by the B binary or this B is the like base. Usually we get a ternary expansion, and you look at each digits. If all those digits can be generated by a finite automata, which means there is a machine can produce each digit of this number, then we call this is automatic numbers. And then result by Adamchevsky, Bourgault, and Luca, and they can show that actually for such class of a number, if it's not rational, then you can immediately get a transcendental number. So this is another dichotomy theorem in this for those functions. So, but today my talk is more focused on the power series. So I think everyone knows this power theory starts from the series result about the power theory starting from Hadamard's PhD dissertation. And in his study.
Sorry, okay. Just one question. Christopher Lloyd, you have a question. Would you like to unmute and ask away related to the previous slide?
Previous slide, okay.
Do you have an analog for D finite?
Yeah, we have this is actually the I forgot to mention. There's a recent paper by Jason Bell and his collaborators, and there's a analog for D finite. So if something is not definite, then if something is definite, then it must be rational. So yes, we will. Yes, there's an analog for this definite case.
Yeah, thank you so much, Shaoshi. Thank you.
And in Hadamard's thesis, and one of the very philosophical question asked by Hadamard is, what's the relation between the coefficient and the function itself, especially singularity? So this is a very general question because actually in this thesis, Hadamard present many results. And especially, he focused on two classes of special power series. I think I select those two classes because there are some arithmetic meaning. So one class is with coefficient taken from a rational number field or integers. Another class is related to probability. So if the coefficient only taken from a finite set, which they call the finitely distinct coefficients. So I will overview some of the classical result for those power series. And the first class is power series with rational coefficients. So all coefficient A and N is taken from a field of rational numbers. And the classical well-known result is due to Eisenstein. So this is about the globally bounded property of algebraic power theory. So if you have algebraic function and then expand it as a power theory, and then you can show that there is a uniform t. When you multiply this tn, then this coefficient will become the integers. That's the if the coefficient is if the function is over qx, and then expansion is usually is a rational coefficient. But then the denominator of this coefficient has this kind of very regular t to the n, which means in the denominator only finite many prime can appear in this. So this is the one of the result by Eisenstein. And then that's my talk abstract. I mentioned the Fatou. So actually, there's a very a classical paper by Fatou in 1906, and this is about the trigonometry theory and the Taylor series of and there's a very nice result. There are two results actually. One is usually in our combinatoric books, they call it Fatou lemma, which is about when a power theory can be expanded as a power theory with integer coefficients. And then the condition is the constant of this Q denominator Q0 is 1 or minus 1. That's the one of the conditions for when a rational function can be expanded as a power theory with integer coefficients. And another result is this kind of dichotomy theorem, so which Fatou showed that for a power theory with integer coefficients, and if because the integer coefficient, if there's infinitely many, and you know that when you take x equal to 1, and this will become a convergent. So it's not so, which means the convergence radius is at most 1. So if this is achieved, if the convergence rate is inside the unity, which means the convergence radius is equal to 1, which in the experimental case, and then Fatou showed that this power set is either rational or transcendental, so which exclude the irrational algebraic case. So this is one of the I think I see the first rational dichotomy, the transcendental dichotomy for power theories, and this theorem actually was enhanced by Polya and Carson. So they can show more than just the transcendental. In the transcendental part, they can say more. So in this same condition, under this same condition, and the Polya Carson theorem say that is either rational or it has this unit disk as the natural boundary, which means if this is algebraic, this must be rational, because algebraic function can only have finite many singularities. So this cannot be take this case. So it's then you force this to be rational. So that's why Polya-Carson is a stronger result than Fatou's result. And another class of classical object studied by the previous researcher is about the power theory with the coefficient from a finite set. And this is actually also the first result also from this Fatou's paper. So in this case, Fatou showed that a power theory with finitely many different coefficients is either rational or transcendental. So you don't need this condition on the convergence radius. So because there's only finite many, so this can only be 1. So this achieved the extremal case, and then you get the rational and transcendental dichotomy. And this result also improved by several peoples. I think I checked some of the classical literatures, and it's funny that there are some from 1917 to 1922 and across many years, and several people write a paper about trying to improve the Fatou's result, and all published in the same journal and with the same titles. And finally, in 1922, the result is due to Ziegel. So nowadays we call the Ziegel theorem, which show that if you have power theory with coefficient from a finite set, then you can show that this is either rational or take this unit disk as the natural boundary. So which is many of results in this dichotomy theorem can be generalized to have this kind of natural boundary result. So this is also kind of a generalization of Fatou's result. And then there's many things we can ask about more arithmetic study of power theory. Is in general, the problem is how you can decide power theory is rational or algebraic, transcendental, or there's another level of transcendental called hypertranscendental. I will explain this later. And actually, there are many results, actually very standard results you can find in this book by Polya and Ziegel, the chapter 3 about arithmetic aspects. So there are many classical results, which I mentioned is in this chapter. So if you're interested, you can have a look. Also, there's another complex analysis book, classical book by Reimers. They also talk about the boundary behavior of power theories, and there's many results. So when I was many years ago, when I was in Fields Institute, so I was reading this book by Reimers. So I was trying to ask myself, can we generalize most of the results into the case of several variables? And that's at that time it's just a long-term project. But now many things can be generalized to the multi-variable case. I will report some of the results. But usually we are not working with very, very general power series. So my favorite power series is called the definite power, which is arise from combinatorial settings. So let me give the definition of this. And the power theory in several variables is definite. D means taking derivation. So if you take the derivation with respect to different variables, and in general, if you collect all these kind of derivatives, it will form a vector space, infinite dimensional vector space over the Russian function field. But in the case when these derivatives form a finite dimensional vector space, and then we call it definite. And in a more specific way to say it is, for each variable, if you take the successive derivative, you will find this kind of linear partial differential equation for power series. That's the definite. And in the one variable case, it just means a power series which satisfies a linear differential equation with polynomial coefficients. That's the value. And this is defined by Richard Stanley in 1918, and in this classical paper. And actually, the motivation for this is this kind of theory appear quite often in combinatorics counting. So that's why he used the name of this power theory. And also, there's generalized to the multiple case by Lipschitz, and there's many arithmetic and algebraic property of such class of power theories. And recently, my collaborator in Linz, Manu Kawas, and wrote a book on this. And this book contains about more than 600 pages. And there are a lot of things to tell about the definite functions. And also, if you want to see more combinatoric study of this definite function, you can read Richard's book and also Manu's monograph. So, and let me roughly explain, how large of this kind of a class of the power series. Sure, algebraic function is definite because this was originally proved by Abel many long time ago. And this class of power series actually is closed under taking some product and some this. And also this include very classical hypergeometric series, which is appear in combinatorics and special functions. But not all functions is definite because there's one property in the univariable case. Definite function can only have finite many singularity or finite many poles. And then you can see that from this analytical property, and one of sine x is not definite because there's infinite many poles, and you cannot get the definite. And there are many things not definite. And from different in the previous many years, and the people from study this class of power theory from different angles. And when I was a PhD student, I was mainly working this kind of power theory from the computer algebra point of view, with designing algorithm to manipulate these kind of functions. And also I did some analytical combinatoric things about these definite functions. And most recently, we focused on this arithmetic property of this definite power series. So in our opinion, I think this is kind of very rough analog between the algebraic number and definite functions. Sure, you can replace this by algebraic function, but I think its better analog is definite function. It's more like algebraic number in the power series settings. Okay, as I said, the goal of our long-term project is try to extend most of the classical result from univariable case to the multivariable case. And actually, the classical Poirier-Cartan theory has been studied extensively by people from several complex variables. And there are some people like Martineau and Straub, and they already extended the Poirier-Cartan theory to the several variable case. And many years ago, I think, when I was in Waterloo with Jason, and we managed to extend this result under the assumption that the given definite function, given power series is definite. So we show that this is kind of analog of Fatou's result. So if you have a multivariate power theory, but with coefficient from integer ring, and if this power theory at the same time is definite and converge, replace the unit disk by polydisk, and then we can show that actually this condition, those two conditions will enforce this power theory be rational. So that's quite a first kind of rationality theorems we got many years ago. And there's another classical, as I said, is work about power theory with coefficient from a finite set. And this is reproved by Van der Borden and Shaplinsky in 1994. And this is if you have a power series with coefficient from a finite set, and actually you can replace this ring, a field of rational number by any field of characteristic zeros. And if this power theory with coefficient from finite set is at the same time definite, which means this satisfies a linear differential equation with polynomial coefficients, then this power theory must be a rational function. So that's actually follow from Ziko's theorem. So because definite function can only have finite many singularity and cannot take this unit disk as the natural boundary. So this must be rational. So that's short proof for this result. Follow from. And then with Jason in 1917, and we generalize this result to the multivariable case. Actually, we are trying to rewrite everything, but actually the proof is become more and more complicated than this one. So the result is now you have this power theory in several variables, x1 to xd, and the coefficient is still taken from a finite set. But we need to assume that this finite set is in the field of characteristic zero. So this is in the positive characteristic case, this is not true. So we need this condition. And then we show that if this is a definite power theory, and then this must be rational. So that's our second rationality theorem.
Sorry, Yoshi. There is another question by Christopher Lloyd. Christopher, would you like to unmute and ask your question? If your mic is working.
Yeah. Which slides?
Hello?
Yes.
It's working? Okay. Thank you. You said that you like to think of definite as being the correct analogy for algebraic numbers. I was wondering why not periods?
Oh, periods. You mean
it seems like the appropriate analogy would be, algebraic functions are algebraic.
So, in algebraic number in the case of in the setting of numbers and in the setting of power theory, when you work with power theory, what I say is most of the natural algebra of algebraic number I think is definite. That's what because when I formulate some of the statements, I usually replace not just by algebraic functions, but by definite functions. This is always more properly formulated.
Okay, so you think so you don't think that the correct analogy would be periods, because the class of definite functions is closed on the integration, right, and derivation.
Yeah, yes. But the period is, you mean a number, still a number. I mean, here, in the setting of a power theory.
Yeah, the analogy.
Functional. Yeah, yes. Yeah, I think the period is good analog extending these algebraic numbers, yes. But it's more general, yeah. I think that the motivation for thinking about this try to generalize. So with Jason, when we try to generalize this result, we have our motivation. I think one of the simple motivation is trying to understand the integer point. And so you have given a variety, and we are trying to think about how this integer point distribute among on this algebra variety. And the way to describe this kind of distribution is used so-called least integer function, which is kind of putting all the integer points encode this coefficient information of integer point with this power series. So the idea is quite natural. This is given you have collect all the non-negative integer points, so n1 to nd, and then you associate a monomial, and then you take in the sum over all the integer, such kind of integer points. Sure, you will get a power theory in several variables. And now you can ask some very natural question. So when this power theory become a rational, whether this is rational, Taylor expansion of a rational function. So I think the why we ask this question, because if this is rational, and then you can show that actually the non-negative integer points will distribute very regularly, so-called semi-linear, like arithmetic high-dimensional analog of arithmetic progression. So that's why we care about whether this is rational or not. But actually this is very hard because given a variety how to decide this rational, in general this is even impossible. So we can ask a weaker condition because rational is too restricted, and you can ask whether this is definite, which is in a larger class of power series. But actually turn out that with the previous result, you can show that because this only either 1 or 0, so this is from a finite set. And then you can show that definite is equal. And then with these things, you rational not, it actually is undecidable. So this actually you cannot easily check this is the rational not. So. But there are some result we can get because, for instance, in the curve case, if this is a curve, and we can see more. So if this is a curve, and you can also if this unit function is rational, and then we can characterize this curve actually. So that which we can get is this curve, the defining polynomial will factor into the following form. So where the f is very regular, is this called the integer linear form, and the g has only finite many zeros. So once we know this is rational, and then actually we can say something about the curve. But in general, that's fine. For instance, if this is not of this form, like x squared minus y, this is not an integer form and also has many not finite many zeros, and then you can immediately claim that the unit function this is not rational, and then immediately you can get that this is not definite. So you can see some property about this unit function by looking at the form of this the defining polynomials. But this is only for the curve case, so we don't know more than the curve case. And there's more general definition called definite, more than definite, a larger class of process is called a d-algebraic. So the definition of this is as follows. A power theory is d-algebraic if you can also take the successive derivative of this power theory formally, and if we view this, then you generate this over the rational function field. If this field has transcendental degree, has finite transcendental, in general, you have infinite many derivatives, and the transcendental degree in general is infinite. But if it is finite, the transcendental degree is finite, and then we say this is called a d-algebraic, which is a differentiable algebraic. And this is a more general class of power series than definite. In definite case, you just think about it, generate this as a linear space, but now you generate it as a field. If the transcendental degree is finite, then this is d-algebraic. Or in another sense, in the universal case, it just means this power series satisfies an algebraic differential equation with polynomial coefficients. And we have, with Jason, we have quite a broad conjecture. I think this is far from being proved. So given a power theory, given an algebraic variety, and we still think about the integer points, how this integer point distribute, and we look at these unit functions. And we already show that if this is definite, and this is equivalent to the rational. But actually, I think this equivalence is stronger than, I think we under this assumption, we conject that this is d-algebraic if and only is rational, which means if something is not rational, then this power theory will not satisfy any algebraic differential equations. This is our conjecture. But for the moment, also we can only prove this conjecture for the part of the case of a curve case and reduce the problem to the understanding the integer solution of pair equations. So that's the ongoing work with Kovaya from the Udine, and we are still working on even the curve case. So. And there are some example like as an example which I showed before. So like x to the this, and we know that this is the unit function is not a rational. Actually, you can show this is not a d-algebraic by using some result due to Mahler. And the idea to prove this is satisfy no algebraic differential is following. If this is a d-algebraic, then the specialization at some at some value, like you take y equal to 2, you will get the univariate power theory. And then there's a result by Mahler. If this satisfies algebraic differential equation, then the coefficient cannot grow too fast than some power of m factorial. And then you can conclude that this not the algebraic. So this is just for this example. So we use this kind of Mahler's estimate from his transcendental number theory book a lot to study this problem. So this is just one simple example I can show. And there's another funny conjecture due to Chola, also about the algebraic things. So we can show that by using some modular form arguments. We can show that x to the n squared is actually satisfy an algebraic differential equation of order, I think it's order 3. But then when you replace 2 by 3 or more, 4, 5, and the conjecture is this is not a d-algebraic. And this conjecture also far from being solved. So for the moment, I think we can only understand this, why this is d-algebraic, by using some argument from modular forms. Okay, now let me turn to another more coefficient level understanding of definite power theories. So this is so now you take the coefficient of a definite power theory, and the property of this coefficient sequence is so-called p recursive. So this is you have a sequence. If this sequence, sure, for sequence you can shift. So if you shift finite many times, and they satisfy this recurrence. And so in another word, this just means a sequence satisfy a linear recurrence relation with polynomial coefficients in n. And then this is called the p recursive. And if those coefficients p0 to pd are constant, not free of n, and then we say this is called C finite, or in usual naming is called a linear recurrence, if it's equivalent to the C finite. And Stanley in his classical paper showed that the power theory is D-finite if and only if coefficient sequence an is p recursive. So p recursive in the univariable case, they are equivalent. So they are the same object. Also, let me recall that if this is C finite, then we know that in this level is rational. So this is why this is also another. But this correspondence will not hold in the multivariable case, even for very simple example. For instance, if the coefficient is of this form, 1 over n1 square, and this is very simple coefficients, and they satisfy many, with each variable, they satisfy a first order linear recurrence. But the general function is not definite. So this is actually very complicated power theory. So for definite power theory and also for rational function, when you expand as a power theory, and the coefficient has very strong structure. So in the C finite case, if you have a linear recurrence and over the field of character 0, and you can look at the place where you get 0. So this you can try to understand the 0 structure of this sequence. And there's a classical result, so-called Skolem-Mahler-Lech theorem. So it says that this 0 set actually is is a finite union of arithmetic progressions, which means it's very structured. It cannot be a very the 0 will not appear very randomly after finite many steps, finite many turns. For instance, for this sixth order recurrence, this is the linear recurrence with coefficient are free of n, this constant coefficient. And then given this initial values, you can show that actually for this sixth order, you can show that the 0 set is this single set 8 and this order numbers. So this is this is holds for the general things. And then there's a conjecture by Rubel. The conjecture is whether this still true for this p recursive sequence, which means now the coefficient is no longer constant, is depending on n. And this conjecture also is not solved; it's still open. And actually, you can formulate this conjecture as a linear case of so-called dynamic model line conjecture. I will not explain this in this talk, but actually there's a book by Jason Bell and his and Yoka and Duca about the dynamic model line, and they also explain this. And there are some cases are already solved. For instance, if the leading coefficient is constant, say it's 1, and the second coefficient Pm is a non-zero constant polynomial, which means the first two coefficient is a constant polynomial, and then this conjecture is true. So that's the and then recently there's another result about if this sequence has taken from some finite geometric group, and then this conjecture is true. So this is first this result was proved by Bezivan in 1989. So when the coefficient belong to this finite geometric abelian group, and then this is this conjecture holds. And with Jason and his student, and we reprove this conjecture using the some technology from algebraic dynamics. And with this new proof, I think in this univalve case, and later on, Jason and they can extend this result to the multivariable setting. So which means this new proof leads to the multivariable generalization of this classical result. Okay. Now let me come to the last part of my talk. So in general, we try to solve this conjecture, but then we cannot solve this directly because, and then there's another way to partially solve this conjecture is given a D-finite. This is about D-finite Power theory, and with coefficient P recursive, and we want to see under certain condition when this P recursive becomes C-finite, which means sometimes you need if for a sequence, if you can say you can make the order higher, maybe you can bring this degree of the coefficient down to the constant. So this is so we trying to understand under certain mild condition whether this P recursive will become C-finite. Then you can show this Lubel conjecture will hold by using the classical Scholar-Mallet theorem. And that's why from that on, we trying to study when the D-finite become rational. This is why we and now we need something from the some terminology about the height, but that's quite common knowledge for number series. So height is just a measure of average complexity of algebraic numbers. So for algebraic number, so if the given minimum polynomial with the integer coefficient, suppose that the conjugate roots is beta 1 to beta d, and then you can define this kind of size of this algebraic numbers by taking this product. And then if you take the logarithm derivative of this divided by the d, take the average size, and then you get the wave height. This is very standard definition of the wave height. And especially for rational numbers, actually just how many digits you need to write down this numerator and denominator. So that's the bit size of this rational numbers. This is the height. And with height, then you can generalize some of the classical results, which I proved with Bell in 2017 and in 2019, and they can generalize this result. So what they get is under some condition about height growth, and for this for given a power theory in several variables, if the height of this coefficient grows not faster, I mean divided by log n, is grows slower than this log n. I mean the 10 to 0, which means is much slower than this log n, and then this is rational. So this in our case with Jason we prove if the coefficient taken from finite set, sure the finite number is definitely grows. This condition must definitely satisfied. So this result generalized our previous result. And also amazingly, I read some of the related paper by Dimitrov about the proof of Schinter-Zassenhaus conjecture. Actually, this result inspired some of the idea in the Dimitrov proof. So this is very nice. So there's some this kind of power theory result can help prove this classical conjectures. And this result also was improved later by just in the second paper in this series paper about this rationality and definiteness. And the second result is when this is still you work with this coefficient from a number field, and for the definite, and assume that this sequence is also definite. Now the question is how this coefficient grows. There are some gaps. So the first, if this is satisfy a linear p-recursive sequence, and you can roughly estimate the height will not grow faster than n log n. This is easy to estimate. And there are also the growth can be have different patterns. So, but then the amazing result due to in this paper is say that actually there are some very gap structure. So either this grows like n log n. If this not of this order, and then boils down to the log like a growth like a height growth like. So there's only three kind of pattern. One is this growth like n log n, or growth like n, or log n, or then is finite and with also some density estimate for this. There's some upper density estimate for this growth. But this is also still actually still a open question, because you think that for a p-recursive sequence, when you look at the height, and there are only 4 type height growth can happen. So this is still not fully understand. But for some other setting, like about Mahler case, in the Mahler function case, the coefficient, and there are some 3 kind of pattern, and this kind of gap structure was understand for Mahler function, but this is not understand for the definite power series. So somehow this is quite a natural class of function, but still for the coefficient growth, it's not clearly understand. So this is the question which proposed by Bell and Nguyen and Zannier about the height gaps for the coefficient of a definite power series. And very recently, we can show the level around here. So if this Boston is if this level is Boston to here, and then we can show some rationality. So recently we show that if you have a power theory with coefficient from a number field, and at the same time this power theory is definite, and then if the height growth is O capital this n, and also now we need another condition about because in general this is algebraic numbers. There's a denominator, so we need also have some control about the denominator. So the denominator can be very complicated. But if this LCM of the denominator has also some this growth, with those two growth conditions, then we can show that this definite will become rational functions. And moreover, and we can show that this rational function actually has very special denominator. Actually, the denominator can only be kind of a root unity. In the uniform case, the root of this denominator can only be a root unity. So that's the another property of this rational function, if this rational. So that's the another rationality. So in another way, for Lubel conjecture, if such kind of growth satisfied, then this become rational. Then the zero structure of this coefficient must be a union of finitely arithmetic progression. So that's the. In somehow we confirm some of the cases of Lubel conjecture for definite power series. So that's the. But the Lubel conjecture is still far from being proved. Even when definite is algebraic power series, we don't know whether a Lubel conjecture is true or not. So that's the. And another related problem about the power series is so-called Hadamard product. So this is a very natural product for two power series. You take the coefficient-wise product, and there are many property about the Hadamard product. the one of the simple property is if both FG are rational power series, then the Hadamard product, when this is n, which means the number of variables, if in the universal case, the Hadamard product of two rational functions is still rational. But when you replace, it's still in the universal case, if you replace rational by algebraic, then it's, in general, it will become algebraic. And if you take the Hadamard product of two algebraic power series, and in general, this is no longer algebraic, maybe a transcendental. So that's, and in the bivariable case, the Hadamard product of two rational power series in general is algebraic. And if you replace this rational by algebraic, even in the bivariable case, this may be a transcendental. But there's a very deep result in the class of definite power series. The Hadamard product actually the definiteness is closed under taking Hadamard product. So which means for any definite power for the Hadamard product of any two definite power series is still definite. So this definite is stable under taking a Hadamard product. But it's very there's a funny conjecture, which is also our starting point, try to understand more about this rational transcendental dichotomy phenomenon about Hadamard product. This starting from a very a conjecture by Stanley in his paper about the definite power series. So this conjecture is following. So we know that when you take the general function of 2n choose n, when k is 1, you know this is algebraic power series. This is and the conjecture is when replace this here the exponent, if the exponent is greater than 2, then this immediately will become transcendental. So this was originally a conjecture by Stanley, and then this conjecture was proved by Felagelet in 1987 using some analytical method. Basically, the idea is to do the asymptotic of this coefficient, and then you can conclude some transcendence. Another proof is by Woodcock and Sharif. They use periodic analysis to prove this transcendental result. And we are trying to, I think, at least about 2 years ago, when Umberto visited me in Beijing, I have some discussion with Umberto about this Hadamard product. I think my feeling is we are trying to show that that's the only case you can get. That's the, I mean, we are trying to show this example actually is quite universal, which means we see everything from this example. So let me to be more precise. So one of the results at the beginning, actually, we have the following conjecture. It turned out that this already proved in 1992. So the result is following. So if fx is a definite power series with rational function, rational number coefficients, and if you take the Hadamard product of itself, if you take the Hadamard in general, this is definite. But if this is rational, then we show that one can show that actually this fx must be rational. So which means when this is the Hadamard product of f itself is simple, then f itself must be simple. And actually, with Michael Singer and Umberto, we found two proofs. It turned out that this from this I think we discover later when we have the proof and we looking for some literatures, and we found that actually this theory was already proved by Benzahu and Bezivan in 1992. At that time, the Piso's the conjecture about the piece root of this is conjecture is not proved because Umberto proved this conjecture. And with the method from Umberto's paper, I think we can give a much shorter proof of this. And another thing is amazing thing is that by using some difference Galois theory, which means Galois theory for the difference equation, because the coefficient, definite satisfy P recursive sequence, it will satisfy linear recurrence. By understanding the Galois group of this linear recurrence, and we can also prove this rationality result. but there's another conjecture also, at least is asked by Umberto to me. So I don't know really this is, but maybe some other already asked this question. But this conjecture actually is about whether this is the very general phenomenon. So that this conjecture is if fx is algebraic. So we know that the Hadamard product of algebraic possibility in general is not algebraic. But if this Hadamard product is algebraic, and then we conject that I think fx can only be rational. So because you know the rational Hadamard product of two rational is rational, but then the conjecture is say that if something is simple, then must be very simple. So that's the conjecture. Because if this conjecture, I think this is a way to generalize this conjecture. Because 2n choose n x1, you know, the general function is algebraic function. It's not rational. So the power must be cannot be algebraic. That's the. And for this conjecture, I think I'm still working on this. It's funny that this conjecture can have something to do with gamma values, some algebraic relation among gamma values. So I will try to work more on this. So maybe that's all for my talk. Thank you very much.